Good morning, everybody, or almost noon. I'm going to try and be within my 10 minutes, and I've done this presentation 2 months ago in California. It took 20 minutes, so I'm going to go fast, and I'm going to need you guys to be focused. Okay, so here we go. So in quantum transistor, we have a very simple mission, simple to understand, very not simple to execute, is build an integrated single-chip quantum computer. So what do I mean by that? This is a IBM quantum computer. Inside that box is everything Alon showed you 3 presentations ago in his first slide, the chandelier, the control, everything. That person is my size. And that system doesn't do anything practical yet. What it does do is cost about $100,000 per qubit. Somebody said today we don't talk about money here. Well, let's do. So in 4 years, when they have 1,000,000 qubits, how much is it going to cost? How big is it going to be? Maybe if Alon is very successful, it's going to be smaller, but maybe not. So our vision is simple. We want to take this thing and put it in a chip. This has happened before, 45 years ago, when IBM had a very big mainframe, and Intel came in and gave us the 8086 and put the computers on our desks. Today, they're in our glasses, in our pockets, everywhere, right? We want to do this for quantum. That's our vision. So why do we want to do this? Would have been obvious, but let's talk about it for a second. You don't make a sale without having ROI. ROI depends on 2 things: the value you create, the R, and the investment you are requiring from your customer, the I. And nobody in quantum today talks about ROI. They only talk about getting there without thinking about how much is it going to be and what value it's going to create in what applications. To be able to cross the chasm, and I think that chasm is going to be very deep in quantum, you need something you can mass produce, you need something you can drop down the cost per qubit to a level that will enable multiple applications to get positive ROI. This is our mission. We don't want to be first out there. We want IBM to get there and sell $50 million computers, $100 million computers. We want everybody to be in pain. And then we want to come in and say, okay, this is something we can manufacture in a semiconductor fab at volume and at a price point that will be able to answer multiple applications and do the same thing that happened to the computing market, classical computing market, as happened in 1980. So 3 years ago, when we started doing this, people said, look, this is crazy. There's no way you're going to put this behemoth inside a chip, and this is going to work. A lot of these people still say that, but they're less sure of it today. What we found there then there was no modality that would enable us to do this, so we had to think about a combination of different things to create that modality. There was also the problem of control that Alon just mentioned and mentioned very well. Today, control doesn't scale and cost by itself tens of thousands of dollars per qubit. And if you want to bring everything down to a decent price per qubit, you have to deal with control. So our control needed to be integrated inside a chip. We need to figure out a system that will do all these. So now you're clear about what we're trying to do and why we're trying to do it. I'll have maybe 3 minutes to say how we're trying to achieve that. So this is a qubit, our qubit. You can see by the scale of 1 micrometer there that this is about 4 micrometers on 1 micrometer. And this is manufactured in our own semiconductor fab here in Israel. This is not silicon. This is made of diamond. Okay, so this whole device, which is both an optical device, a quantum device, and an electrical device, there's a transistor in there, there's a qubit in there, there are waveguides coming in for single photons and for lasers, and all of that is made in diamond in our own fab in Binyamina, by the way. If somebody is living north of Tel Aviv, we are recruiting. Okay. We'll talk about that toward the end. So the first building block, our qubit technology, works anywhere from room temperature to 4 Kelvin. 4 Kelvin is just as low as we care to cool it down. Has great performance across that range. It will need to be at 4 Kelvin to start with quantum computing, but we'll be pushing that temperature forward. So both an electrical, optical, single photon device and a quantum device in one package, okay? So semiconductor in diamond using also photonics. So what kind of performance can you look for something like that? Well, we performed on this device a 2-qubit CNOT, And these are the fidelity numbers that you see down there for room temperature and for 4 Kelvin. It takes way too much to explain this, but there's an archive article, an archive paper, which explains everything we've done to get there. And if you're really interested, 35 pages, the physicists are probably going to think it's a short story. Okay, so when we have those qubits, how do we connect them? Through photonics. Okay, so this is a SEM photo of our first silicon photonics chip that is basically a host to these qubits. It allows connectivity of these qubits, any-to-any connectivity right now, not sure in the future. But the whole thing, you can see how big it is because there's about 8 qubits that fit in here, in that little piece. So the secret sauce of our technology is a combination of diamond qubits, okay, solid-state qubits. We're talking about atoms and electrons. We're not talking about, photonic computing. This is solid-state spin qubits. And they're connected by photonics, so we don't have to move them. In Tal's presentation, he told you how hard people who are using metric qubits are having to move them around to be able to create connectivity and entanglement, and we don't do that. We do distributed photonic entanglement, which allows us to keep our metric qubits in the same place where we manufacture them in the chip, and still be able to connect them through entanglement to other qubits. So that's basically the two things that we've changed to be able to break the mold of the system that we have today. So in terms of innovation, this is not a datacom wavelength silicon photonics. This is a visible light silicon photonics. This is something you don't really see every day. You're starting to see more of it because of wearables. But right now in the market, 99% of silicon photonics is for data communication. So we had to redesign everything for visible light. It's a single photon switch. The qubits on the left will output a single photon that will go through, hold that switch, and then they will meet together through a Bell measurement to create entanglement, and that's the most technical thing I'm going to say here today. And in this POC chip are 16 qubits in 2 groups of 8, where you see the nice green lights, and the connectivity is any-to-any, okay? So there's a lot of molds being broken here, innovation done to be able to break the equation that systems are dealing with right now. So the full chip, the architecture, this is the silicon photonics part. This is where the qubits come in. And then eventually, not immediately, we'll go for integrated control. I have been talking to Alon about it. 2 minutes? I'm almost done. I've been talking to Alon about it. There's a lot of work being done on cryosymos. We're not going to invent the wheel here. We're going to partner. But it is imperative that if we want to scale up the system, the control has to be inside. Alon is perfectly correct on this. Without that, you will not be able to either scale or price point that will make you in the market. So in this system that we're building right now, you can achieve 25 qubits per square millimeter, which is the size of the chip. If you're building a bigger chip, you'll have more qubits. You can scale it up with better photonics, and there's a lot of other technical details we don't care about right now. So 2 words before I have to finish about the company. We were founded in 2023. Our headquarters is in Binyamina. So anybody that can do something in quantum and lives north of Tel Aviv should really talk to me. I will save an hour and a half of your life every morning and another hour in the evening. And we're looking for a physicist, quantum optics physicist, and we're looking for process people because we have our own fab. This is a photo for from a fab in Yamina. We need materials PhDs. Some of them can be physicist materials, kind of involved, but clean room experience, making chips experience, okay? We are leading in Israel today, and that's the last propaganda you'll see here today. IIA consortium that is dealing with developing semiconductors in diamond. Why? Because it's great. And there's a lot of companies already involved, about 11 industry companies, including Rafael and Elbit and NVIDIA. A lot of academics involved from every university almost in Israel, 11 academics. And with that group is working with our fab as infrastructure to develop multiple applications of semiconductor, not just quantum, power delivery using diamond MOSFETs, photonics to be able to move a lot of power of lasers through a small chip. All of those things are happening. We also are hiring people to serve that community, specifically within our fab and our chip design area. And we have committed to getting some people to do that as well for everybody else. So if this is interesting to you, please come talk to me.